Hi, I'm Paris, and this is Lab 4 Circuits and Capacitors for Physics 2212. Just a quick introduction to this lab. One, we used a circuit construction kit to explore time-dependent voltage and current in a DC circuit, and then we used the CCK to understand how batteries, capacitors, resistors, light bulbs, ammeters, and voltmeters affect a circuit. Benefits of this lab are that this allows students to see the interactions between the different parts of a circuit. In the first part of this lab, we created a circuit in the CCK with two 1.5 volt batteries, one 47 ohm resistor, one 100 ohm resistor, and two ammeters. Shown to the right is the circuit with the different parts labeled. My prediction was that the ammeters would read about 0.02041 amps from the shown calculation. And my prediction was right because in the model, the ammeters both read 0.02 amps. If the ammeter's connections were reversed, the ammeter would read negative 0.02 amps. Shown in figure 1 is the top ammeter replaced with a voltmeter. This reads positive 3 volts because the potential at the red probe is higher than the potential at the black probe. Figure 2 shows the bottom ammeter replaced with a voltmeter, and that reads negative 3 volts because the potential at the red probe is lower than the potential at the black probe. Figure 1 shows the original circuit, but now with one ammeter at the bottom. Moving from A and going clockwise around the circuit through each point gives us the total potential difference around the circuit. The notable potentials are from A to B across the batteries, which was negative 3 volts, from C to D across the 47 ohm resistor, which was 0.959 volts, and from E to F across the 100 ohm resistor, which was 2.041 volts. From the loop rule, we know that the potential difference for a round trip around a circuit should be 0, and by adding up the potential differences from the left, we get 0, so the loop rule applies for this circuit just as predicted. Figure 2 on the bottom shows a graph of the potential versus position around the circuit, and the calculations at the bottom right are the resistances for the different parts of the circuit. So the resistance of the 100 ohm resistor, the resistance of the 47 ohm resistor, the resistance of the wire, and the resistance from the ammeter. Now we made a slight change to the circuit. We removed the top ammeter and added one in parallel with the 100 ohm resistor, and the current now reads 0.06 amps. This can be explained by the node rule, which states that the current into a junction or node equals the current out of a junction or node. And in this case, the current into the junction with the ammeter is 0.06 amps, which is why the ammeter reads 0.06 amps, and then the current out must be the same thing. In part 2 of the lab, we deal with a circuit with one 9-volt battery, one 10 ohm or 20 ohm light bulb, and one 200 millifarad capacitor. Figure 1 shows the circuit with the battery connected, and we can see that the capacitor charges and the light bulb lights up, and then the bulb slowly dims as the capacitor charges, and then the bulb is no longer lit when the capacitor is fully charged. In figure 2, it shows the circuit with the battery disconnected, and in this case the bulb lights up immediately and then dims as the capacitor discharges. The bulb then shuts off when there's not enough charge of the capacitor, and the process is finished when the capacitor is fully discharged. I noticed that the current flowed in the direction from the positive part of the capacitor to the negative part of the capacitor. In figure 1, the time to charge the capacitor with the 10 ohm light bulb took about 2.33 seconds, whereas with the 20 ohm light bulb, it took about 3.87 seconds. And in figure 2, the time it took to discharge the capacitor with the 10 ohm light bulb was about 9.26 seconds, and with the 20 ohm light bulb was about 18.89 seconds. Time-dependent voltage across the discharging capacitor. Using a circuit with one 9-volt battery, one 30 ohm light bulb, and one 200 millifarad capacitor, we took 20 seconds worth of voltage versus time data, and we plotted the natural log of the potential difference divided by the potential versus the time. This plot provided us with the slope of our graph, which was found to be negative 0.1667. Understanding that the time constant is equal to the resistance times the capacitance of the circuit, the calculated time constant was found to be 6 seconds. Using the fact that the slope of the graph is equal to the negative inverse of r times c, we found that the time constant was 5.9988 seconds, which is almost 6 seconds. So this means that both methods are quite accurate in finding the time constant. To conclude this lab, there are a couple questions that can be answered. To answer the first question, we could say that with a real-life ammeter, there is a non-negligible amount of resistance, so our results would change. This would probably cause the total resistance in our circuit to go up. And to answer the second question, without a resistor and using a real battery, the capacitor would reach full charge much faster. And this is because the resistor provides resistance against the current, and without it, the resistance would be almost zero.